So first of all, uh, what does it mean by a graph? Okay. So the theory of graphs generated from a very well-known problem, and it is known as Königsberg bridge problem. Okay, and the problem was that you have four islands, suppose denoted by A, B, C, and another one, suppose D. Okay, and this is a river. Okay, and in between these islands, so this is your island A, this is island B, this is island C, this is island D, and these islands has been connected by some bridges. Suppose this A and C has been connected by two bridges, B and C has been connected by two bridges. Okay, A and D has been connected by one bridges, B and D has been connected by one bridge, and also C and D has been connected by one bridge. So you can go from any island to other through these bridges. But the question is that the problem has been asked that if you start from any island, is it possible for you to come back again to the same island A by crossing every bridge exactly once? ওকে, বোঝা গেল কি বলতে চাইছি? মানে এ আইল্যান্ড থেকে স্টার্ট করলে you need to get back to the same island by crossing every bridge exactly once. মানে একবার মাত্র তুমি ওই একটা ব্রিজকে ক্রস করতে পারবে। So that was the problem, and the problem is that the question is that is it possible or not? Okay, দেখো বোঝা গেল কিনা আগে কোয়েশ্চেনটা? Okay, and this problem has been unsolved for 150 years. Okay, and it has been solved by the great mathematician Euler in 1736, and he proved it through a new kind of approach, which is today we are calling it graphs. Okay, so the problem is that to start, I should write down the problem. Start at any of the four island. Yes, Okay, any of the 4 island, that is, you can start from C, you can start from D, you can start from A, you can start from B, but you need to get back to the same island. Okay, so to start at any of the 4 island, okay, and walk over each of the 7 bridges, right? You have 7 bridges through which the islands are connected. So each of the 7 bridges, you need to walk over each of the 7 bridges exactly once and return to the starting island. Okay, without any other ways. That means the possible ways may be swimming. So without swimming across the river. Okay, so without swimming across the river, of course, right? So this was the problem, and the problem is that is it possible? Okay, and that problem has been solved by Euler in the year of 1736 after being posed 150 years ago. Okay, so that's a very nice problem, but no one before Euler put it to some concern. And this problem has been solved by a very beautiful way, and which we are calling it today graphs. Okay, so the graph theory has been generated from this very well known problem, although at the beginning it was not known that this will generate a very nice subject of mathematics. Okay, so Euler represented the problem by means of a figure. Suppose in the problem we didn't mention anything about the starting point and ending point, right? So you can start from any island. Suppose you start from A and you can start from here, right? So that doesn't mean that where did you start from, that is, you can start from this point, or wherever it is, but you need to start from the island A. So that was fixed by the problem. So Euler, what was his thinking? That he thought that this island A can be thought of as a point. Okay, this island C can be thought of as a point, B can be thought of as a point, D can be thought of as a point, and in between these points you have connectors. Suppose these are edges. Okay, we call them edges, right? So this was the figure. Sorry, this is B and this is D. Okay, so he drawn this figure, and vertices, that is A, B, C, D, represents the island areas, and the edges represents the bridges. And Euler proved that the solution of the Königsberg bridge problem does not exist. Okay, there exists no possible way. Okay, solved by Euler Euler in 1736. Okay. So this problem can be analogously stated as the problem of drawing figures without lifting the pen from the paper and without retracing a line. Okay. So the same problem occurs when you pose this kind of problem, that draw a figure without lifting the pen from the paper and without retracing any line. Okay. So this problem, so there exists no possible way of returning to the same island. Okay. By walking over each of the 7 bridges exactly once. So this problem generates a very nice subject of graphs. So here this figure contains 2 objects. One is the vertices, that is A, B, C, D, and you have edges, right? So generally we define, so formally we would like to define a graph by means of 2 objects. One is the vertex and another one is edge, right? So let us define a graph means, so graph denoted by, we shall denote a graph through G and put in the brackets 2 sets, one is V, another one is E. Okay, so graph which is denoted by this consists of 2 sets, a vertex set of all vertices, suppose we denote it by V1, P2, Vn, and an edge set. Okay, E1, E2, En, where each edge, if you look at the edge here, suppose you look at this edge, so this edge has 2 vertices, one is A, another one is D. So these 2 vertices are called endpoints. Okay, so where each edge consists of two vertices called its endpoints. Okay, and we write it as, suppose E is your edge, then you write it as, suppose, U V. Okay, or similarly VU. So both are same. You may mention UV, you may mention VU, whatever. So this one. Okay, so you can write it in this way, UV. Okay, and if if E equal to UV, that is E is the edge whose endpoints are U and V, then U and V are called adjacent, in the graph G, and also we say that the vertices u and v are incident incident to the edge E. Okay, as you have specified that E is equal to UV. Okay, so in this way you can define a graph which consists of a vertex set and an edge set. So a vertex set is a finite set, that is consisting of finitely many elements, suppose v1, v2, vn, and edge set is also a finite set, e1, e2, en. Okay. So here in the above example, these are your edges, and these are your vertices. Okay. So here your V is A, B, C, D, and your E is this one. So we can write it as, suppose this is your E1, E2, E3, E4, E5, E6, E7. Okay, so E1, E2 up to E7. So this is your graph G V with respect to this problem. Okay. Okay. A graph sometimes it is called a linear complex. A graph is called a linear complex. Okay, or a one complex, or a one dimensional complex. Okay. Okay. Now note that you may come across some kind of situation where in graph you will face that an edge has endpoints that are equal. That is, you may start from some vertex and end up at the same point. Suppose this is your vertex U. So this kind of edge are called a loop. So note that a loop is nothing but an edge whose endpoints are equal. Okay, whose endpoints are equal. Okay, and you may come across some situation exactly. Okay, in this case, you see that between A and C there are two edges, right? So these two edges are called parallel edges. So this kind of edges are called parallel edges. So we may again parallel edges, or one may say that multiple edges are those which have same pair of endpoints. Okay, and for example, if you take two vertex, okay, so these are parallel edges, multiple edges, something like that. Okay, so a graph without having loops and multiple edges are called simple graph. So a graph having no loops and multiple edges are called this is called a simple kind of graph, a simple graph. Okay, because it has no loops, no multiple edges, and otherwise it is called a multigraph. It is called a multigraph. Okay, now someone may feel that between two vertices, these are, so you may draw any kind of connector, maybe a straight line, maybe a curve, whatever it is. Okay, maybe something. Okay, suppose one may, so this kind of thing. To specify that, yes, there is an edge in between these two vertices. So you do not need to think about what kind of curve is this. No. Okay. Okay. So for example of simple graphs, suppose you may draw some kind of graph like this. So these are simple graph because it has no parallel edges, no loops. Okay, so these are all simple graphs. Okay, and sometimes these are called suppose, so these are called, so these are multigraphs. Okay, so these are all multigraphs. Suppose you can make a loop here. Okay, so these are multigraphs. Okay. Okay. Now, as whenever we are defining some sort of sets, we may be concerned about the subsets, right? So here also, if you think about a graph, then you can certainly think about some kind of graph which is kind of subgraph, right? So what does it mean by a subgraph? So a subgraph, okay, so let's have a let's draw a picture. Suppose you have this graph. Okay, this is a graph, suppose, yeah, okay, this one. So this is a graph, suppose GV, so our V is, so let us denote this vertices as V1, V2, V3, V4, and you may denote it by E1, E2, E3 and E4. Okay, so this is your, so V is your V1, V2, V3, V4, and E is your set E1, E2, E3 and E4. Okay, so this is a graph you have considered. Now you would like to define a subgraph of this graph, then what you will do, you may take a subset of this V. Okay, suppose you take V star, so take suppose V1, V2 and V4. Okay, now you need to take the edges as which is certainly be a subset of E, but you need to take that subset from this E, that is, suppose you have already considered this V1, V2, V4. So now see that you may take so V1 to V4, suppose you take U1 and you may take E2. Okay, so this is a subset of, so this is a subset of V and this is a subset of E, and this V star and E star will generate a graph. So here it is V2 and V4, right? So this is V1, V2, V4. So this is your U1 and this is your U2. So this is a subgraph. This is G star, V star, E star. So this is a subgraph of the original graph. So what is the definition of subgraph? So a subgraph of a graph GB is a graph G star, B star, E star, where V star is a subset of V and E star is a subset of V. Okay, so this is the definition of a subgraph. Okay, now so suppose this is definition A. Now we'd like to specify another kind of graph. Now suppose you take a graph this one. Okay, and yeah, so you specify the vertices and specify the edges. Okay, so this is your GV. I'm not going to write down. Okay, so let's V is V1, V2, V3, V4, and E is E1, E2, E3 and E4. Okay, now with respect to this graph, you may consider the same set of vertices and draw another graph. What is that? Suppose you have specified all these vertices as that of the graph G, but whenever you are to consider the edges, you are taking the complement edges. That means the edges that are not in that graph. So which are those? Right? So here you are considering those edges. Okay. Yeah. So this is your another graph which is denoted by G bar, V, E bar, and this graph is called complement graph, complement of the graph G. Okay. So what is the definition? So the definition must be like that. So let GB be a simple graph. I need to take simple graphs that is having no loops and parallel edges. Then its complement denoted by, in the complement graph your vertex set is same, but your edge set is the complement of the edge set E, right? So that is why it is called complement graph. So denoted by this, so its complement is again a graph having the same vertex set as G, okay, such that two vertices of V are adjacent. That means there is an edge in between two vertices adjacent in G bar if and only if they are not adjacent in G. Okay, that means the edges that are not in the original graph. Okay, so this is called a complement graph. Okay, okay. Now another kind of graph we may consider, which are called induced subgraph. That means it is a subgraph where not only your edge set is a subset of the original edge set. Now let us try to explore an example. Suppose okay, so suppose it is okay, V1, V2, V3 and it is V4. You have considered this graph, and you have also, you can specify the edges, which is E1, E2, E3 and E4. Okay, so this is your graph. Then you may consider a subgraph that means you may consider this subgraph. Suppose you take this one, that is V1, V2, V3, and in this subgraph you need to take the edges. That is, if V1 and V2 are adjacent, then in G, then they should be adjacent in this graph also. That means you need to consider all the edges that are present in the original graph for these vertices. Okay, so this is your subgraph where the vertex set is V dashed and edge set is E dashed, and this V dashed is V1, V2, V3, and your edge set is also a subset. That is, it is E1 and it is your E2 and it is your E3. So E1, E2, E3. So this is also a subset of B, and this is a subset of B. Okay. But the condition is that this subgraph is a special kind of subgraph, because here you need to consider all those edges that are present in this graph for these vertices that you have considered in your subgraph, that is V1 and V2. If it is adjacent in this graph, then you need to consider the edge here also. Since V2 and V3 are adjacent through this edge E3, so you need to consider this E3 edge in this subgraph also. Okay, so you need to consider all those edges that are present in the original graph for the concerned vertices. That means you can write that. So the definition can be, so these kind of subgraphs are called induced subgraph. It is an induced subgraph G dashed, V dashed, E dashed of a graph GV is a subgraph of G such that any two vertices that has been considered, any two vertices, suppose U and V that are adjacent in G dashed, if and only if they are adjacent in G. Okay, that is UV, the edge UV belongs to E dashed if and only if the edge UV belongs to E. Okay, so this kind of subgraph is a special kind of subgraph of the original graph, and these are called induced subgraph. Okay, and lastly, now for the time being, we may consider another kind of graph where every edge, any two edges are adjacent. Any two edges are adjacent, and these kind of graphs are called complete graph. So, okay, we need to consider a simple graph where any two vertices are adjacent. Okay, so a complete graph or we name it as a clique. A clique is a simple graph such that any two vertices are adjacent. In the graph. Okay. That means suppose you take three vertices. Yeah. So this is, suppose this is V1, V2, V3. So here any two edges are adjacent because there is an edge in between them, and this complete graph is denoted by K3. So for three vertices, we denote the complete graph of three vertices as K3. If you take four vertices, then this is called K4, where any two edges are adjacent. Okay. If you take five vertices, suppose Okay, so any two vertices are adjacent, so okay, and there must be another one. I think now it's okay, right? Okay, so this is your K5, and certainly, okay, so I would like to draw K6, K7. Okay. So complete graph with 6 vertices, complete graph with 7 vertices, and generally, sorry, a complete graph with n vertices will be denoted by Kn. Okay. 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 Now let us try to now. Is a very interesting fact is that if a simple graph is given, then corresponding to this graph you may associate an n cross n matrix. Okay, that means suppose you have a graph where the number of vertices are n, then this will associate a matrix of order n cross n. Okay, but what would be the matrix corresponding to a simple graph? Suppose, so these are called, these matrices are called adjacency matrix. Okay, so let GV be a graph, be a simple graph. I do not, I need to specify it, be a simple graph with the vertex set V having n many vertices. Okay, n many vertices. Okay, now we define a matrix. We define a matrix. Suppose we denote it by AG, whose entries will be denoted by Aij n cross n, where your entries has been defined as, so Aij, and this will be 0 if I equal to j. Okay, Aij will be 0 if I not equal to j, and for this corresponding I and j, for your vertices vi, vj, if they are not adjacent in the graph, that is the edge vi, vj, this will not be there in the graph. Okay, and Aij equal to 1 if I not equal to j, and Ti Vj, the edge, is present in the graph. Okay. So in this way, you can consider a matrix whose entries Aij can be defined in this way by means of its edge set and vertex set. Okay. Suppose, look at the example. Suppose for example, let us consider a graph. Okay, suppose we consider a graph with 4 vertices, this one. Okay. Now let us denote this as V1, V2, V3, V4. Okay, and your edges can be written as so E1, E2, E3, E4, E5. Okay, so where you may specify these edges as in terms of the vertices. So E1 is V1, V2, right? E2, V2, V3, E3, V1, V3, E4, V1, V4, and E5, V5, V3, V4. Okay, so these are your edges. So with respect to this representation, you can so the graph, so the adjacency graph, adjacency matrix of the graph G is, so your AG is, so what you do, you just write down the vertices in the row, in the column, and also in the column, in the rows. Okay, then as you have represented here, so what you would like to do, so your diagonals must be 0, right? Here I equal to j, so aij's are 0, so you may put 0 in the diagonals. Okay, and then you just write down the corresponding entries for which you have edges. So your V1, V2 is an edge. So where do you find your V1, V2? Now here V1, V2 means V2, V1. So these are same. So your V1, V2 is here. So this is 1. Similarly, V2, V1 is also 1 because they are same. Now you see that V2, V3. So your V2, V3, where it is V2, V3. So this is 1. Now V3, V2. So here, so this is 1. Okay. Okay. Now V1, V3, V1, V3. So here it is V1, V3, and your V3, V1. So it is also 1. Okay. Now V1, V4. What is V1, V4? So this is 1. So V4, V1. This is also 1. And also V3, V4. So where it is, so V3, V4, this is 1, and your V4, V3, so this is also 1, and the rest are 0. So this is 0, this is 0. Okay, so you have that matrix. Okay, so this is your matrix. So it is 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0. So this is the adjacency matrix corresponding to the graph given above. So corresponding to any simple graph, you can associate a simple graph with n vertices. You can associate a n cross n square matrix whose entries can be defined this way. Okay. So I would like to stop here.